this has come up a couple of conversations, and people have asked me questions about basically is Enceladus young or old? And so this talk is probably the most radical departure of any of the talks in this whole workshop. It's not just planetary science, it's astrophysics, but I'm going to try to make it relevant and not go overboard. I mean, the idea, I mean, we're all interested in water-rock interaction on these bodies, but so my question is, like, what is the rock and what is the water? And so we are talking about places with the exception of Enceladus, we have no direct in situ measurements of any of the components. Everything is remote sensing, whether it's Enceladus or Ceres or Europa. So anyway, so where's the controls? Okay, let's see. Yeah, this works. Okay, so this is a testament to human ingenuity. There are so many models now. As I was telling Everett over lunch, by the time I was done with this talk, I knew less than I started out with. So I'm going to talk about sort of like the traditional way we've looked at satellite formation, which we still think applies to Europa. But then when we get to Enceladus, there are these other ideas that Enceladus might have been kicked out of Saturn's rings at some earlier stage, or there may have even been a catastrophic rearrangement of the inner satellites of the Saturn system. And of course, all of this has implications for the composition, we think, but it's hard to figure it all out. And it's even harder to figure out how to test some of these ideas. But just to back up, just think about it, right? Jupiter and Saturn, Europa and Enceladus, they're part of satellite families, right? They're all prograde, they're going around, they're in the planet's equator. So we always start with these sort of general nebular hypothesis ideas. That is, when you have a system like that, you have some sort of dissipative disk of some combination of gas and dust that is settled out, condensed, and accreted into the satellites we see. So these days, when people model the formation of a giant planet, they usually form a giant planet core, which at a certain point begins to hydrodynamic collapse of the solar nebula gas that's circulating the sun, the early sun, the protosun, begins to fall upon it. So you have something like this. This is just typical from a recent paper. Do I have any kind of laser? I probably. All right. So this is just blank in the center, but the sun's in there. This black thing is a gap. Jupiter is actually here, and it opens a gap, but the gap is incomplete. Material continues to flow across the gap. And in this series of images, you see a different calculation where we're zoomed in on the gap. There is Jupiter, and each one of these boxes is a factor of 2, just like in the old movie. And what happens is material comes in and is, in fact, circling proto-Jupiter in this calculation. And this is the sort of proto-Jovian nebula if it were to get cool enough or accumulate enough solids that are flowing in from the solar nebula, can build a satellite. Now that's the top-down view. On the right is a vertical slice through a similar calculation by some different workers. And if you can see these arrows, that's Jupiter in the center. This is a slice through a nebula like this, a proto-satellite nebula, and the arrows are pointing up and down because that's the sense of gravity. So material is coming in from this side and also raining down on this nebula. And this sets the stage then for what I would call traditional or primordial satellite birth. That is, this is happening at close to t equals 0, just in those first few million years of solar system history where we even have a solar nebula. Okay, so and this is a classic now paper that goes back to the early aughts by Robin Canup and Bill Ward, where they built an analytical model of material flowing in a gap to make the Galilean satellites. Here's kind of a cartoon from the paper of material is coming from above and below. It viscously flows into the planet and out away, and material continues to condense and satellites grow. And there's a series of papers that are well known in the field. And the figure on the right is just one example possible calculation of the temperature profile both through the midplane and through the optical surface of this, in this case, a particularly thin disk that would match the overall density pattern that we see in the Jupiter system, which of course is very famous. You go from the all-rock Io to the somewhat icy Europa, and then to the much icier Ganymede and Callisto, and this corresponds to these various temperatures. And this is all wonderful, and there's a series of these papers, and it should work for all of the giant planets. It should work for Saturn, and in fact there are models for Saturn, but there are complications. Before I get to those complications, though, let me tell you about something that this is a figure that I put this in because Mike Zielinski showed this. Okay, this has to do with something that we call the Warren gap. Okay, Mr. President, we cannot accept a Warren gap. Anyway, it has to do with different isotopic systems that can split up the different meteorite classes. And Paul Warren wrote a paper a few years ago about this, but now this has become a very big deal. Maybe some of you have seen or heard about this paper that was in the PNAS by Croyer et al. The idea is that there's basically two broad classes. You see one class, the isotopes are not even relevant here. I'm not a cosmochemist anyway. But basically you have the ordinary chondrites, you have the Martian rocks, you have the Earth, you have uralites, which are carbon, but also carbon-rich bodies. But then you have all these other carbonaceous chondrites, and they form these two distinct groups. And this has been interpreted as actually two distinct zones developing in the early solar nebula. And here's, in fact, a figure from Croyer et al. And so here's another, this one is in terms of just molybdenum isotopes. It's even more complicated than what Mike said. It's not just ordinary chondrites versus carbonaceous chondrites. Each one of these classes has its own flavor of irons. There are irons with the ordinary chondrite group, which are non-carbonaceous, NC, and there are irons with the carbonaceous chondrite groups. If you had asked me naively about the early solar system, I would have assumed the iron meteorites all came from, the cores of parent bodies that melted very early by aluminum-26, and this all happened close into the sun, and we're just looking at the remnants. But in this, there seem to be two distinct classes, and because of the timing and the short-lived radioisotopes, they can separate the times of the formation of these bodies. And so this figure on the right is from the same paper, and it actually shows what their concept is that first the irons, the non-carbonaceous irons are forming, that is melting of parent bodies. Then Jupiter begins to grow, and it brings that gap in, and that splits the solar system in two. Then you have iron bodies forming outside Jupiter, and then finally the open circles are the ordinary chondrites or the carbonaceous chondrites, depending on which side. So this is and the time scale you can see here is over the first few million years of solar system history. So this is rather extraordinary, frankly. We can go farther. This is a paper that's been submitted. I don't think it's been accepted yet, at least I don't know, in which Steve Desch at ASU tried to take these kind of concepts and look not just at the isotopes, but at the either the presence or absence of calcium aluminum inclusions, which occur in these late forming carbonaceous chondrites, as well as chondrules, which occur in most or abundant in most carbonaceous chondrites. And in his model, what this graph shows actually is the calcium aluminum inclusion to total solid weight ratio as a function of distance from the sun in this model. And Steve does have Jupiter forming at 3 AU. I mean, he knows where Jupiter really is, but it's part of one of these models where Jupiter migrates. But anyway, that's sort of a small detail. But he has, these are ordinary chondrite classes, HL and LLs. There's Jupiter. CMs and CVs, these are chondrite classes that have CAIs and chondrules. And he has them forming basically in a pressure bump in this model that it's stabilized outside the Jupiter gap. Okay, so that's this is the mental concept. These are, and the reason I'm bringing this up is that this is sort of state-of-the-art work. The idea is that these are where the solids that are building meteorite parent bodies that can ultimately provide material for the satellites like Europa that are being built right around Jupiter, what they're actually made of. In this model, CI chondrites, which is a favorite composition of mine personally, because they're so chondrule and CAI poor, Steve just says they must form farther out, maybe by Saturn, and then he just sort of wanders off. It's incredible. So I wouldn't have necessarily thought this before, but maybe it's true. Saturn is a very interesting situation, right? Saturn is not as massive as Jupiter. Saturn does not open the same kind of gap as Jupiter, at least in the models that have been built so far. Here's a typical calculation of a body forming on a normalized distance of 1, and this is a surface density profile, and it just depends on what the mass of the central body is, and basically the lower the mass, the lower the gap in total sort of depth is. And I put these red arrows to point. These are half a Jupiter mass. Saturn is a third of a Jupiter mass, and so Saturn opens a much smaller gap than Jupiter. And here's a separate calculation that Alessandro Morbidelli sent me, where he has Jupiter and Saturn forming at a certain resonant position. So here's Jupiter's gap, there's Jupiter, this little bump in the center is actually the accumulating mass around Jupiter that will build Europa and the other satellites. And Saturn is kind of like this sort of satellite bump, not as deep. But the interesting thing is this would be the pressure bump where Steve would hide his CAIs and his chondrules, and Saturn then would probably accrete a lot of material from outside its own more shallow gap. But there's even more. Once these sort of giant planets begin to form and open these gaps or partial gaps, they really stir up the remaining solar nebula. And there are several papers you can find now in literature. This is just one of them from a couple of years ago. So here's Jupiter, here's Saturn. This is a static calculation just over 1.5 million years. These are color-coded planetesimals that have very low E and I. And then over time, as these bodies grow in size, their sizes are, the dots are scaled to their mass, it scatters things everywhere. Carbonaceous bodies that are near Jupiter scatter into the inner solar system and out to Saturn. Carbonaceous bodies, if such exist right near Saturn in this concept, will also scatter and pollute Jupiter, as well as the asteroid belt and even the terrestrial region. So there's be a mixing of carbonaceous chondrite classes as feedstock for both Europa and Enceladus implied by these kinds of models. But there's a problem. It's fine for Europa, but it's not so fine for Enceladus. And the fun thing about the Saturn system is that it's beautiful and articulate, and it has all these crazy satellites, giant Titan, all the small mid-sized satellites, distant, Iapetus, and all the rest of it. The thing about the Saturn system is it's not just 4 giant moons, it's 1 giant moon, Titan, and a bunch of mid-sized moons. And if you go in from Titan, the mid-sized moons decrease in mass, that's what this graph here is on the right, in total mass, and it slides all the way down to basically to the edge of the ring where they're tiny little ring moons. Not only that, but as you get closer to Saturn, everything gets icier. It's not absolutely monotonic. Maybe most people in this audience probably know that Enceladus is a pretty rocky body. Nearby moons, Mimas and Tethys, have much less ice. This is a silicate fraction, much less rock. But if you look broadly, the rings of Saturn are nearly pure ice. Mimas is nearly pure ice. Enceladus has rock, but the next one out, Tethys, is the iciest of them all, and it has much more mass than everything on the inside. Anyway, so the inner part of the system is extremely icy. You go out to Dione and Rhea, they have a decent amount of rock, and then you get to Titan, and it really is much more like Ganymede and Callisto, such as you saw in Steve Vance's talk yesterday. So this is different. These models of inflowing material that build satellite systems don't differentiate easily between ice and rock, and you would predict that the inner satellites would be just as rocky or rockier, like at Jupiter, okay, than the outer ones. So how do you get all of this ice in the inside? Well, Robin Canup attempted to solve this problem a few years ago, and many people in this audience may already know some of this work. The idea, well, one of the things that happens in the what's called the gas-starved disk evolution model is that satellites grow and they migrate into their parent planet and are destroyed. Okay, Jupiter is left when the gas eventually all goes away, or is slowly the solar nebula, basically is photoevaporated and basically the lid goes off the problem. It stops. you have 4 giant Galilean satellites left. At Saturn, you only have 1, and sometimes it just works out that way. This is just one. This is an example calculation she published. If you can see, the green stars are the actual moons of Saturn, and then the black dots are scaled by mass and planetary distance, and these bars indicate their eccentric excursions. At a certain time frame in the calculation, there are in fact 4 Galilean-style moons, but by the end of this one, there's really only 1 left and some smaller ones closer in. So that's good. You actually have small ones close in, but they would still be made of ice. But the important thing is that the other 3 up here all slid into Saturn and were destroyed. But how were they destroyed? Are you standing there for a reason?
5 minutes.
Oh, just sit down, you. All right, all right. This is part of this paper, is that this is a smooth particle hydrodynamic calculation. As long as Titan can differentiate, at least partially, then as it goes into the Roche limit, it's first will strip off the icy mantle and then the rock core, because Saturn is so fat at this time, because it's warm, will actually fall into the atmosphere of Saturn before it's tidally torn apart. So all of these small particles are icy particles, and then the idea is that these particles will form the rings of Saturn, and then as they spread, they will give birth by gravitational coagulation to a series of small satellites that will be tidally driven away from Saturn. And that was a TBD part of the paper, but then other people, in fact, were working on something similar. This is Charnot et al. This is a model where they, in fact, have a massive ring, and they ask the question, if we let this ring spread viscously through interparticle interactions, what kind of moons will we get? And what happens is that you basically cough up a giant cosmic hairball, which you might want to call Rhea in this model, and that gets rid of a lot of mass. Plus there's mass also viscously evolving into the planet. You cough up another satellite, number 2. And this goes on down the line. You basically make a series of smaller and smaller moons. And as long as there's some rock around, maybe it's irregular amounts of rock, you can maybe explain you can explain the iciness, you can explain the mass pattern, you can explain the overall iciness, and maybe if you're lucky, you can get the stochastic rockiness of the inner satellites. But the thing is, it takes time, and the distance between, let's say, the birth of Rhea and the birth of something like Mimas or Enceladus could be on the order of 1 billion years. And this would apply to the Knupp et al., the Knupp model, which forms the massive ring at t equals 0, basically, due to the sort of this Titan-like body being destroyed. Or it could also apply to more radical ideas, such as the tidal stripping of an icy mantle of what we call a centaur, a body from the Kuiper belt that is passing by Saturn during some early epoch when the solar system is very dynamically unstable, such as in the famous Nice model. Oh, and here's, in fact, a recent paper that attempts to model the tidal passage of a body passing near Saturn, where an icy mantle is partially stripped off, and you end up, after lots of collisions, making an icy ring. So this then totally decouples the time frame of the inner moon's formation from the formation of Saturn, except maybe it would apply to the timing of the Nice rearrangement, which could be coincident with the late heavy bombardment in the inner solar system, or it could be much earlier. It's very inefficient, and there are lots of problems with this, and don't want to even give you the impression that I think I even believe it, but given time, if you want to ask me questions later, we can come back to this kind of idea. This is connected, at least in many people's minds, with ideas about the overall evolution of the satellite system. We believe, determined how fast the satellites of Saturn are evolving away from Saturn due to tides. And this is driven by what we call Saturn's tidal dissipation, or its Q, its big Q. If you take these numbers that are published by Laney et al. In 2017 and then run the clock backwards, you find that these are the positions of all the inner satellites. You find that they all crash into Saturn in much under the age of the solar system. The same thing happens to the moon if you take the tidal Q for the Earth right now. So we know that the tides on the Earth are due to rearrangements of the continents and dissipation on the seafloor and turbulence and so forth. So we know it's time dependent. We also have models of time dependent or frequency dependent Qs for Saturn, which in fact prevent this catastrophe and in fact allow the satellites to smoothly go back to basically just somewhat closer to Saturn over 4.5 billion years. And you can find the details in a paper that Francis Nimmo and Amy Barr and other people we put together for the Enceladus book that Paul is one of the editors of. So we don't actually know. And this is also connected to ideas which I won't go into right now about whether the rings of Saturn themselves are very young, which is a whole other can of worms. Anyway, so let me just, because I'm short of time, let me just sum up saying, when and how was Enceladus formed? This is, to me, one of the most interesting questions, and this is the one I have come to the point where I hope you know less than when you started listening to me. But anyway, it could have formed primordially in Saturn's subnebula along with Titan and its other satellites. This is the traditional view, the primordial formation. Or it could have formed out of a massive mega ring earlier in Saturn's history, but not at t=0. It could have been part of the formation of all of the small moons up to Rhea, which is the mid-sized moon that's just inside Titan. Or it may just be part of a compact cluster. This is what Robin Knupp would prefer, of Mimas, Enceladus, and Tethys. And she would explain the rockiness as either partial disassembly of a proto-Titan-like satellite, or maybe there's a published with Julien Salmon of contamination of heliocentric rocky debris later on. Or it could be, even like I just mentioned, from ice from a tidally stripped centaur body. And then there's this other idea that the satellite system we see today is actually it's not the original satellite system. That is, there was a much stronger evolution in the past, which would lead to resonant crossing and catastrophic disruption and reassembly. There are reasons I think this is probably not true, but is any of this testable? Well, I'm out of time, but we at least have information from Enceladus about compositions from the INMS and the CDA instruments, and you've seen some of this earlier. We have detections of carbon dioxide, of methane, of ammonia, and of course, of hydrogen. Perhaps even more important, and I'll just skip this, perhaps even more important, we have measures of D to H. There was one particular pass deep into the plume where we could actually measure both hydrogen and HD and get a good ratio. And this is the Enceladus number plotted against everything in the solar system. Meteorites, the Earth is here, the protosolar nebula. Enceladus sort of fits in with outer solar system bodies. It's comet-like. Does it mean it's built from captured Centaur material? Well, we don't really know, because captured Centaurs would be really Jupiter family comets, and they have very divergent D to H measurements. Although the only one that's done in situ was done by Rosetta, and that's 3 times basically 3 times solar D to H, whereas Enceladus is 2 plus or minus a large error bar D to H. The one thing I think you can really rule out is a kind of model where Enceladus would have condensed out of a hot nebula around Saturn. That would have driven reequilibration of deuterium in water to closer to a protosolar value, and that's not what we see at all. And I'll just stop there, and because I just want to put these ideas out. It's like it's a monument again to all of these ideas that are churning now. I won't say this is a big controversy. It's just that it's really an unsolved problem. Okay, and I think in the future what we can look forward to are detailed isotopic and compositional measurements at Europa to actually begin to really understand some of the things that are going on, at least in one place in the outer solar system. And of course, we have to go back to the Saturn system in some case, and Ceres, don't worry. Okay, thank you.